Okay, now that you've seen that experiment, I'm going to explain to you what you've seen. The point of that experiment was to see how streams develop if you have a slow, consistent moving stream, okay? And then in flood stage, and then if the stream is cut off, and then if there's a catastrophic outflow like an end moraine breaks or something, what happens? And then the calming from that, after the flood recedes, you know, what patterns develop. And actually, I was really shocked to see that I honestly thought that after the flood, the big flood in that video, that the stream would try to go its original course at least somewhat, but it went in a totally different direction. It went from east to southeast to northeast flow. Now, there are some things to remember about that experiment. It's a good, decent experiment, but I was using sand, okay? Now, there are several things that affect that textbook drawings, and I showed you in illustrations, I showed you how streams develop. The key things to remember, most streams flow over, like when you're doing that textbook example, the stream is as if it was flowing over a cohesive soil or over bedrock, okay? Cohesive soils will be things like silty clays and clays or sandy clays. We gotta have clay to have cohesiveness. That experiment I just showed you was done in uncohesive soil, sand, okay? But it did still develop a meander, as you saw. Just wasn't a really good one. And the good thing about using sand instead of clay is that the experiment can take less time to run, and my water bill doesn't end up being $700. But the things that can affect the development of a stream, all right? We have the velocity of the water that's being put into the system, okay? Into the stream, all right? If you have, like after a spring thaw from the mountains and that's where your stream starts, you're gonna get a lot more water coming down a lot faster than you would if it was just a normal summer day, okay? So the velocity of the water is important. The stream's load is important. And what do I mean by load? Well, these two are closely related. The load is what's floating in the water. I'm not talking about the fish or the plants. I'm talking about the sediment, okay? Is it mostly fine clays, okay? Is it mostly pebbles or sand, all right? And that depends on the velocity, because the faster a river is moving, the larger the particles it can carry, and the further downstream it can put them, all right? And that experiment showed you that with that little lake. Once the stream hit that lake, that baseline, it just dropped all that organic debris because it couldn't hold it anymore. Okay? Now, not only that, but we have the geology, which affects the load. Okay? Now, what do I mean by geology? I'm not just meaning about what that stream is carrying. Is it silt? Is it clay? Is it sand? Is it pebbles? Is it boulders? I'm talking about the geology the stream is actually flowing over. All right? Because in that textbook example I showed you, that assumed a homogeneous path that the soil was moving over. You know, like a consistent sandstone or consistent glacial till or something like that. Something that didn't have a lot of variation in it. Now, say you have, and I'm going to show you this, what I mean, an actual real world example of this. But say, okay, remember my thing on geologic maps? Say you're looking down, this is your map, okay, and you have some beds like this, okay, you have some beds like this, okay, you have your strike and dip over here on this bed is maybe 3 degrees, okay, and let's say this is we'll use R for resistant, okay, we'll use N for not resistant, okay, say your dip on this bed is maybe 11 degrees, okay, say your dip on this bed, and this is very resistant, we'll say, relatively speaking, very resistant, we'll say this is a 21 degree dip, and then this dips, this is not very resistant, and it initially will dip, we'll say it dips 20, but then as you get down over here it dips less, and there's a reason why I'm writing these spread out. It dips maybe back down to 7. All right. How's that going to affect our stream? Well, in the textbook example, and we'll say the topography is relatively even. We'll say the topography maybe varies 10 to 30 feet over this whole area. So we're not going to have a lot of topography. So according to our textbook definition, if the stream isn't going at a baseline, it should be flowing straight, all right? But in this situation, it's not going to do that, all right? You have a very slow, so your stream, I'm going to actually use red. I apologize for my blue not working. So my red is going to be my stream, and it's going to flow from this corner to this corner. Oh, remember I always said you need a north arrow? There's your north, okay? So it might do a little meandering here, might not. This is a resistant bed, okay, remember that. This bed is not very resistant, okay, but it dips a little more, so the stream isn't going to meander as much. Then it's going to hit this, okay, all right. So it's going to cut that V. This is where you're going to get to V, but it's not going to necessarily go straight through. It's going to encounter this and maybe go like this. It's going to follow the point of least resistance until it can find a way through. So that was the low area. Say our topography over here is, 50 feet above sea level. Right there, it's 30. So it found its way through. So it looks like we have a meander, but we really don't, okay? And then it hits here, and it's going to first drop that load on that shallow slope, and you'll probably get some alluvial fan deposits. So the stream might braid for a little bit, and then it will most likely follow a nice meandering pattern out. Okay, that's how your geology can affect your stream and vary from those textbook examples I showed you. Okay, so I showed you what it can affect a stream. Now velocity, I'm going to get back to this because some people might separate this out, but I don't. But this also includes water volume. This can affect, as we saw in the experiment, it can actually affect the velocity. Just because you have a lot of water being pushed into the system doesn't mean that water's moving very, very fast. So it's going to carve different landscapes, like you saw in the video, okay? You're going to get, if you have a lot of water volume, like a dam breaks, that doesn't mean it's going to start down cutting and forming all these V valleys and stuff like that, even if it's way above baseline, because you don't have the velocity. Now, I'm getting towards this because I'm going to show you something, because there's a couple examples, real world examples I want to show you. One is well understood. The second one kind of is, but it's on a smaller scale and it's based off work I did. The third one we're still having problems with. All right, and I ran the experiment because I wanted to show you how we can discern the history of a river or stream based on the surrounding area, how it developed, what we see, you know, in the what we see in the cut banks and floodplains and all that stuff. Now, if a river hasn't hit a baseline, now we're back to the profile view, like you're looking up or downstream, it doesn't matter. If a stream hasn't hit a baseline, say your stream's here, but it can start to meander a little bit, and it will, okay? But, or it has hit your baseline, but now that baseline was a lake, that lake is gone, it's no longer your baseline. Well, it's deposited all these sediments. Okay, this is your river. I'm just gonna use that as your river. Okay, so it's deposited all these sediments, but now it's gonna start down cutting again. Okay, it's gonna start wanting to form that V. Okay, well, these sediments become terrace deposits. They are still there. Okay, it shows evidence that this river was flowing higher in its channel at one point before the baseline was disrupted or whatever, for whatever reason it changed. And then when it reestablishes a baseline, you know, you could erode this side and it comes down and say this terrace is now gone, but it's redone its baseline. Here's your river again, and now it has these deposits. And say the baseline gets upset again, but this time the river's over here when that happens, and you get another V valley. So you know, so even though you had a terrace here, it's been eroded, but you have another one down here. And over time, this will erode. If this valley keeps deepening, what will happen is the rock will weaken and whatnot, and erosion will take place, and your V will eventually widen, and you'll be like, wow, how did such a tiny stream make a valley like this? Well, time, erosion, down cutting, lateral cutting, destruction of the baseline, velocity of your stream, your water load, the geology, all this stuff plays an important factor. Okay, I am going to show you two examples. I'm going to show you some aerial photographs, all from Google, right here. Okay, actually, the Grand Canyon's, I'll show you it first since it's out. I'm going to clip them up here so you can see and compare, but just in case you don't know where it is, as you zoom in, I got in close to the North Rim, as we call it. Okay. Now, I'm going to, okay, you see that right there? I'm going to put that down for a second. And Blackie's on, and oh no, oh my God, come on bud, get off, get off, get off, get off. Okay. Now I'm going to show you the Scablands of Washington, and the reason why I'm using these two examples is because I got in an argument with somebody who claimed that the Grand Canyon was formed in the exact same way the Scablands did, and I'm going to show you why that can't be the case. The Scablands are in Washington, it's Pacific Ocean. Zooming in, zooming in, zooming in. All right, now I'm going to put them up here and compare them side by side. Okay, this is the Grand Canyon stuff. This is the Scablands of Washington stuff, specifically Dremel channel or Drumheller channels. Okay, now I want you to look at this aerial photo. Just look at it. Okay, just take it in. Now look at this one. Take it in. Okay, the scales are not the same. This is about a little over a mile. This is a little over 6. Okay, but you can tell something right away. You can tell, even to the untrained eye, you can tell that this what formed this landscape did not form this landscape. All right, they're two totally different patterns. Now this one here of the Drumheller channels actually fits my flood part of my experiment very well. Okay, because you can see these random braided patterns. You've got one river at present, one meander, okay? But you can tell, you see all these little abandoned channels everywhere. What happened here? All right, there's other features here too. there's giant ripple marks around here. Okay, I mean, ones are like 40 feet in crest to crest. Blackie's knocking things off my desk. You know, so they're huge. So from our experiment, we can deduce that a large amount of water was released very quickly to do this. All right. Even though our experiment didn't show ripple marks, it makes sense that they would be there if a large amount of water, not moving very fast without a lot of velocity, but a large volume covered the landscape. Okay. And that's exactly what happened here. This was glaciated. Okay, this is in Washington State. The glaciers were here. All right, this is the outwash flood channel of Lake Missoula. All right, it was a glacial dam lake that had catastrophic outwash. All right, and down here we have the geologic map. All the references are there. There's the actual website. There's the key to legend if you want to look at it. But you can see the geology. There's a lot of quaternary geology here. All right, there is. You see dunes, stabilized dunes, alluvium, mass wasting, loess, alluvial fans, talus, outburst flood deposits, or catastrophic outwash, same thing. You can see sands and gravels, all right? So there's a lot of quaternary units. There's a lot of stuff here that points to you had a big flood, all right? You had something catastrophically outwash. Now the flood, as I was zooming in showing you the ones, you could tell it was still somewhat localized. I mean, you know, the areas, it's not on a continental scale here. We're talking something that's maybe 10 miles in diameter, okay? But you can see what isn't here? Well, what isn't here? You don't have V-shaped valleys. You don't have well-developed meanders in any of this, okay? And our bedrock is mostly basalt, all right? From the raising of the Rocky Mountains, to put it simply. So that kind of rock is going to erode somewhat easily, okay? So this is what a flood landscape looks like. All right, and we've had times in history where dams have failed and they produce similar looking patterns on a smaller scale. All right, and same thing with even with my sand pit experiment. Similar things happen. All right, so we know this is what you get when you get a flood. All right, what about this? Okay. Okay, so what am I seeing here? Well, I can tell you what I'm not seeing. I don't see massive ripple marks. I don't see braided stream deposits. I don't see a river that couldn't decide on a channel to take before deciding on one. I don't see any of that here, okay? Yeah, the valley's wide. It's not typical V-shaped, but you've got other valleys coming into it. It's not like it's one single wide valley shooting straight across with a meandering stream in it, and you got that typical textbook meandering valley. You don't have that here. You have very high cliffs. You get alluvial deposits coming down, okay, from those cliffs, all right? And if we look at our quaternary units, what do we see here? We see terrace, alluvium, and some landslide materials, which is to be expected if you have vertical cliffs. But if we look at the map, and they're mostly yellows, as properly supposed to be, they're isolated. As we're here, they're all over the place. They're everywhere, okay? And they're just little most of this stuff is bedrock, okay? So what does that tell us? Well, we have a problem here. We have a decently meandering stream that has downcut a huge canyon, all right? And we're going to talk, this is where geology is going to come into this. Okay, so the Grand Canyon, there was recently a proposal made about the year 2000 about something called Lake Biddichochi, which is not on this map. It would be up over here somewhere. But before I get into that, they figured that might have been the source, that was a playa lake that gave way. It had a dam for whatever reason, gave way, and cut the canyon within 5.5 million years. Now the lake age was about the right age. But since that was proposed and people got excited about it, it's falling away again because the Grand Canyon shows very old features as well. A lot more old than recent. But it's not just as simple as that. It's not just as simple as looking at the hole in the ground and going, wow, that's big. A lot of water must have done that. You've got to understand the geology of the area, all right? Now, it sits upon the Grand Canyon. As you can see, it sits upon the Colorado Plateau. Here's Arizona. So it's about right in here, okay? These aren't the same scale, by the way, both those maps. The Colorado Plateau is over here in this map, but look at all this other stuff we've got going on here. We have the Basin and Range Great Basin. Now, this is important because this is an area of active extension. North America's actually gotten wider here over the past 10 million years or so, maybe even a little longer, because it looks like this may be the area of a new rift forming. All right, we don't know for sure. It's showing the very early stages of a rift. Will it continue? Who knows? Maybe not, because you also got a subducting plate over here, but you've also got another rift right here, which is the Pacific Rise coming into North America, which is still actively splitting. And it gets a little more complicated than that, because then you get the San Andreas Fault and all this fun stuff. But the point to show you is the Colorado Plateau is surrounded by very complex geology. It's not a simple textbook flat homogeneous area just with the stream flowing through it. Okay, so in the year 2000 around, a guy named John Douglas thought he had it figured out, the Grand Canyon. There was a lake here, and it didn't catastrophically outwash like you would expect, not like the Lake Missoula thing, but what was holding the lake in, he thought, did release, and it released a high velocity of water, but not a large volume at the time. So what he thinks is the stream came over the plateau and was meandering, and it hit the west edge of the plateau, and it hit a drop off. So it started back cutting and just followed the existing meanders. All right. And that seemed like a pretty good idea. And modern stream velocities of the Colorado River seem to sit there and say, well, you could back work it to 5.5 million years, but it's one thing you learn in geology. It's that the modern measurement isn't what happened in the past. So, but I mean, it looked like a good model, but problems. Lots and lots of problems. Okay, this map is zoomed out even more. The scale is about 13 miles. Okay. So, problems. Well, what are the problems? Well, still, you can see where the lake might have been. You see the valley's really narrow up here. And then it comes down. And you can tell the Colorado River does have a slight meandering pattern to it. Okay? So, what he thought was it just established that meander, started cutting back and following it, and boom, all the way up. But the problem with that is there's several problems with that. If that happened, well, after that lake had drained, if there wasn't a new source for the Colorado River, it just would have dried up and you'd have an empty canyon. That's one problem. Another problem is you look at the landscape. Even if that had happened, you would have had, because of the geology, you would have had some braided stream deposits upstream with alluvial fans, and you don't have those. And you definitely don't have any here. Okay, you don't see any evidence of even a high velocity, low water volume flood, let alone a high velocity, water volume flood. You see none of that here. So we still back to the problem. Like I said, the Grand Canyon has a lot of old features. The geology is also a lot more complex here than it is at the Scablands. What you have, this is a good picture. I picked this one from the Geologic Map of the Grand Canyon. As you can see, your Phanerozoic deposits are mostly flat-lying but your Precambrian ones are not. You have an angular unconformity here. Okay, and here's some cross sections. Okay, so you can see the Precambrian is not flat compared to the Phanerozoic. And remember, I just showed you how the geology can affect the direction a river goes. Now, it would have encountered the Phanerozoic deposits first, the flat-lying ones, however the stream formed, and so it probably started meandering. But when it hits the Precambrian, because it still hasn't established a baseline yet, okay? So when it hits the Precambrian, all of a sudden, those not flat-lying beds start to influence the direction of the canyon. The problem with that model is that it looks like, if you pull back, you see the meanders like here and here, and roughly that pattern is maintained. Okay, so the geology, I'm sure, affected it, but there's another reason. So why would a meander channel be carving such a deep valley if there was no massive flood? Well, there's another simple explanation that actually is an old one that people are kind of coming back to, because it's getting to the point where people are trying to solve this enigma in such complicated, bizarre ways, like rivers flowing into Canada up through Hudson Bay, that it's becoming kind of a mess. Occam's razor, people, right? Well, this area has been uplifted. We know that. As the Rockies formed, the Colorado Plateau has just kind of been uplifted without a lot of deformation. It's just been uplifted. Well, the Colorado River was an existing stream that had a baseline established before the uplift occurred, or at the beginning of the uplift, which began about 70 million years ago. As the uplift happened, since it already had a baseline and a meander pattern established, it would just start downcutting within those meander channels. Because the velocity, even though you got a 10-foot drop per mile, the water velocity, yeah, on a little tiny human scale looks a lot, but it's not a lot of water. So it would make sense if the area was just uplifted over time, that meander pattern stayed intact and just downcut. But that's personally how I think that formed. But it remains to be seen. A lot of the evidence is gone. You got a lot of waste piles. I mean, you got steep valleys in the Grand Canyon that'll just slough off and just bury any evidence, or, just remove it. And that's a problem, but, we try our best, and we have to use what works, and we have to develop a model that will work, okay? So the sure thing about this is this was not formed in a flood event. That was the whole point of that rant, all right? Now I'm going to show you Parfrey's Glen in Wisconsin. Okay, this is actually, before I continue, before I show you Parfrey's Glen, this is a great little publication by the USGS. It's available free online. But it shows you how you can get massive flood events and how we can study them in real time within a human lifespan to see what kind of deposits they make. It goes through a lot of them. This one in particular is one that happened in 1996. They're not all have happened within human history, but the ones they have pictures have. It's got a nice chart that shows you peak discharge, things like that. So, I mean, these are things we can measure. Another glacial burst right there. Okay, so we can actually look at these things in real time, just on a smaller scale. So it's not just like we make this stuff up. All right, so I promised you some Parfrey's Glen. Okay, so this is an excerpt from the 1/24,000 scale Parfrey's Glen quadrangle in south central Wisconsin. What I did here is highlighted the creek path for you in yellow so you could see it more readily, and its baseline is this swamp here. Here's your scale down here in feet. So you can see it's not a very huge area, but there's the quadrangle it's in as well. And I just wanted to show you the topo map real quick before I show you the geologic map I made several years ago, because you can see the contours here are closer together. That means there's a lot of topography right here, and then they kind of flatten out. There's a reason why this is here. You have a lot more bedrock exposed here. This is all glacial lake deposits down here. But what happened is the stream cut through it, and I've been to this canyon. I'll put a link to it in the description, a video I've taken at this place. You have these huge, it's a deep V valley that's not very wide. The cliffs are 50 to 100 feet high, and the valley at most in its widest, when you're actually up here, is maybe 30 feet. So it's a good example of a textbook V cut, but you can see it goes straight and kind of bends, meanders around. Okay, so here at Parfrey's Glen, this is a case of how geology affects the course of a stream. Now, I'm going to show you the geologic map that I made in 2013. Okay. Parfrey's Glen, I actually did take the time to make it nice and blue. The baseline isn't in this, but here you have the scale, the map. I'll put a link down in the description to where you can find this map for free. It's a map I did. But you see here, you see different geologic units. The greens are glacial. The yellow is just stream alluvium. The browns and oranges are bedrock. There's also purple here and over here, and that's the Baraboo quartzite. This is in that area all of us geologists go to. But what you can see here is, you can see I have a strike here and a dip here. So the stream was originally following dip, hit this change in geology, and started following strike for a while before it got into the low-lying glacial lake deposits here, where it started to meander better, okay? Where it started to form a meander pattern, I should say. Now I have cross sections of this. Now you can see my cross section. I have a north-south, A to A prime. I cut this off here, and I have a west to east, B to B prime. 6 times vertical exaggeration. Here's my geologic units. Right there. Sorry, Blackie was just being weird. The cross sections didn't blow up quite right. I don't know why, but here they are. So here's the north to south one. Here's the west to east one's the B to B prime. So you can see these dashed dotted lines here. That's where the beds trend. That's the dip of the beds with the vertical exaggeration. If you squash this down, it's going to make these beds not look so vertical, because they're really not. They're, I believe, 25-degree dips. But since I have vertical exaggeration, that makes the dips look bigger than they are. But it's to illustrate how you have a change in geologic units and dip direction in the rocks. Okay, so what have we really learned about all this? Well, to summarize, what I showed you is the textbook way of how streams develop. Then I showed you ways of how other things like geology, water velocity, all that stuff can alter that textbook definition, if you will, and how streams are a lot more complex than a simple illustration in a book, okay? Then I ran an experiment. My sand pit where my pool was, and we did get, during normal stream time, even though it was unconsolidated sands, we did get some meanders. Once the flood started, not the catastrophic flood, just an increase in water volume. We got the water fill up the floodplain, and meanders changed when that water was reduced, and then the river went dry so we could see some features better. And then we had our catastrophic flood, and then that totally changed the landscape. So that experiment, although is not perfect, it did illustrate how patterns in sediments form due to streams, okay? At different velocities, different water volumes, different topography, not really different geology. It was all pretty much play sand that you buy at the store. But it it did illustrate how the landscape can change and what a catastrophic flood, how that changes a landscape as opposed to just standard flooding or a typical stream flow. And I have Blackie back. He has not been behaving today. He is going crazy. All those background noises you heard, this guy right here. But anyway, I'm going to include some links below. I'm going to include links to the Parfrey's Glen map. I'm going to include links to just my website in general. Some links to my book. And to the video. There's a video I did in the UP. It's my Yooper series. It was the first episode. There's a nice textbook meandering stream in that video, and I'm going to put the link to that too. I would link you to Blackie's fan page, but you know, he gets enough attention. He's a lot more popular than I am. So anyway, that is it, and I hope you learned something. Afternote, Blackie on the desk. People do ask me what this stuff is, and I'm more than happy to tell you. Solid copper candle holder that I made for small, long candles. I am obsessed with copper, as is Blackie, as you can see. Well, right now he's more interested in himself. These are, he's gonna knock everything over, I apologize. These are 1 ounce copper coins. They do make these things. All right. This one here. Just like you could get an ounce of silver, gold, platinum, you can get ounces of copper. And this is an antique. It's copper plated. It's steel inside, but it's copper plated mug. I also have a copper plated food oil can, but that's on display here. That's in the kitchen. This right here is a solid ball of copper. Yes, it's man-made, but this copper is from the native copper deposits in the Upper Peninsula of Michigan in the UP near Copper Harbor. And I don't know what diameter that is. Looks like it's a bit more than an inch. Can't be too much more. Maybe 1.25 inches diameter, maybe an 1.5 inches actually. But it's a pretty awesome and solid copper. I have other copper trinkets as well. I'm only going to show you the copper that's in that tin. So this is why I did purchase this at a touristy place. It's a nice place. If you're ever in Copper Harbor, it's a blue shop. You can't miss it. This is also solid copper. But just like you can buy bars of gold, silver, and platinum, you can buy bars of copper. This is half pound of copper right here. So, yeah, as you can see, I have a slight copper obsession. It's a little bit of a one. But feel free to ask me any questions on anything you might see in the background here about this guy or any of the other ones you might see. I'll be happy to answer them. But that's it.